Let's evaluate this double integral by converting to polar. We have the integral from 0 to 4 of the integral from 0 to the square root of 4y minus y squared of x squared dx dy. Let's use the bounds to determine the region and then make the substitutions and adjust the bounds so that we can use polar to evaluate this. When we look at the bounds for x, that's going to be our left x is equal to 0, and the right side of the region, x is going to equal the square root of 4y minus y squared. Now, in order to graph this, we typically graph y in terms of x, but this is x in terms of y. So we can use algebra to simplify this by squaring both sides, and we get x squared is equal to 4y minus y squared. And then you can rearrange the terms to get x squared plus y squared minus 4y is equal to 0. Then you can use the method of completing the square to get this as in the form of a perfect square trinomial. And if you take half of negative 4, which is negative 2, and add and square that to get 4, you add 4 to both sides of this equation. And then you can write this equation as x squared plus y minus 2 quantity squared is equal to 4. And you should recognize that this is the equation of a circle. The center of the circle is at 0, 2, and the radius of the circle is 2. So we can look at a sketch of this. The center of the circle is at 0, 2. The radius is 2. And the left side of the region is x equals 0, which would be the y-axis, and the right side of the region is this x equals, so it's going to be the right half of that circle. And now looking at our bounds for y, would be your lower bound for y would equal 0, and your upper bound for y is equal to 4. And again, I get that from the outside bounds of integration. So the region that is defined by those bounds is this right half of the circle. When we convert this to polar, we're not only going to convert the bounds, but we're also going to convert the differentials. We need to come up with the bounds for r and theta. So we need to come up with the equation for this part of the circle in terms of r and theta. We can use some conversion equations and take what we have written up here, or even up here, either one, and let's do some conversions with that. In fact, let's use the first one. If you take the first equation and add y squared to both sides, you get x squared plus y squared is equal to 4y. I just took that first equation and added y squared to both sides. Now, we know the conversion equation for x squared plus y squared is equal to r squared. And the conversion equation for y is r sine theta. Now we can divide both sides of this equation by r to get the equation r is equal to 4 sine theta. And you can check that this graph indeed is the same as that half a circle. And if you can graph this with a graphing calculator in polar mode, sketch r equals 4 sine theta, and you'll see that this sketch is generated. In fact, the whole circle is generated. So we need to determine the bounds for r as well as the bounds for theta. So if we slice this like a pie, that little section there is d theta, this big section here is dr. We can say the bounds for r would be your inside radius would equal 0. And then the outside radius is on that circle. So the outside r of that circle is equal to 4 sine theta. And then we need to determine the bounds for our angle theta. Our smallest angle theta would be that theta is equal to 0. And then our largest angle theta would be theta is equal to pi over 2. You can again sketch this 4 sine theta in polar mode on your graphing calculator, and when you use trace and you trace and type in 0, you'll see that the path is at this point right here, and continue increasing while you trace, increasing theta, and you'll find that theta is equal to pi over 2 at that point right there. So now we have our bounds, and then we're going to make the substitution inside of the integral as well. So this is going to be a double integral r, and we're going to replace this x squared with what x is equal to. So that's going to be r squared cosine squared theta. That's one of our conversion equations. And then we're going to replace dx with our differential area. And remember, differential area in polar is going to be r times d theta when the graph is r simple like we have here. So it's going to be in the form of r squared cosine squared theta times r d theta. Our bounds for our inside bounds are for r, and the r goes from 0 to 4 sine theta. Our outside bounds are for theta, and theta goes from 0 to pi over 2. Now we're ready to evaluate this because everything has been converted into polar. So let's start with the inside. The inside here is in terms of r. The differential r will indicate that we're going to take the antiderivative, treating r as a variable and theta as a constant. Well, r squared and r, when you multiply them together, is r cubed. And when you take the antiderivative of r cubed, that's going to be r to the 4th over 4. That's r cubed times what we're treating as a constant here of cosine squared theta. And we're evaluating this at r equals our lower bound of 0 and r equals our upper bound of 4 sine theta. And then finally d theta. When we evaluate the upper bound, replacing r with 4 sine theta, when you take 4 and raise it to the 4th power, and then divide by 4, you get 64. So that's going to be 64 of sine to the 4th power, so sine to the 4th theta, times our cosine squared theta. And then when you plug in 0 for r, you get 0. So we get this single definite integral in terms of theta. Now you can use some substitution methods here, actually power reducing formulas maybe, and integrate this, and you will get 2 pi. You can also use the integration feature of a graphing calculator to evaluate.